Okay, this is our first podcast on thermochemistry. Alright, so energy is defined as heat and work. Heat, which has a symbol of Q, is energy used to cause the temperature of an object to rise, and work, with the symbol of W, is the energy used to cause an object that has mass to move. You probably remember from middle school that energy can come in two forms, potential and kinetic. There's lots of ways of classifying energy. This is one way, potential energy and kinetic. If I have a ball on top of a hill, by virtue of its position, it has potential energy. If that ball gets pushed, that potential energy becomes energy of motion, known as kinetic energy, and the ball rolls down the hill. So potential energy is considered stored energy, and we in the past talked about it as based on its position, but it also is based on chemical composition. You'll see why that's important for us. Here's an example of stored energy that is being transformed into energy of motion, and the energy was stored via chemical composition. Talk about blowing stuff up. Alright, so as you probably also remember, kinetic energy is the energy an object possesses by virtue of its motion, and the formula for kinetic energy is 1/2 mv squared, m being the mass and v being the velocity. It's important that you recognize what the units of energy are going to be, specifically for kinetic energy. We use all SI units, and because mass SI units are kilograms, velocity is distance over time, and those SI units are meters in seconds. So it's kilograms meters over seconds squared. This unit, kilograms times meters squared over seconds squared, is also known as the joule. Symbol of J. 1 joule is 1 kilogram meter squared over second squared. A joule is a really small unit of energy because it takes 100,000 joules to heat 1 cup of coffee, to go from room temperature to boiling. So let's go ahead and figure out a kinetic energy problem. So we want to find the kinetic energy of an argon atom moving at 650 meters per second. And you're given that 1 AMU of any atom is 1.66 times 10 to the minus 24th grams. So we've got to get the mass of that argon atom in kilograms, right? Because that's the SI unit. So we're going to use Ke equals 1/2 mv squared. And in order to find the mass of the argon, we know how many AMUs it is from the periodic table. We know how much an AMU weighs. We know there's 1,000 grams in a kilogram. So this gives us the mass of 1 argon atom. And then if I plug it into the formula, 1/2, which is 0.5, my mass is, I just calculated, and my speed was given to me, and my velocity, 650 meters over seconds, and this whole thing gets squared. And when I do that, I end up with 1.4 times 10 to the minus 20 kilograms times meter squared over second squared, which is the same as 1.4 times 10 to the minus 20th joules. So not very much energy, but of course we're talking about a little tiny baby atom. It used to be that the common unit called calorie was what was mostly used when we talked about energy. Still pretty widely used today, and a convenient thing to know is that 1 calorie is 4.184 joules. And we'll use that along the way because we use calories so much in the U.S. But outside the U.S., a lot of other countries don't use calories anymore. They use the SI units. So here is a can of Diet Coke from, I believe it's somewhere in Europe, and it's a low joule cola, not a low calorie cola. Okay. And the calorie was defined as the heat required to raise 1 gram of water by 1 degree centigrade. Now, if you think about how many calories you have in a snack that you eat, those calories that are listed are really kilocalories. So if you're eating something that says it's 200 calories, it's really 200,000 calories with a small c. A big C is the same as a kilocalorie. Okay. It's important when we're talking about energy that we define the system and the surroundings. So in this case, we have a gas inside a container that has a piston. The system is the molecules, what's going on with the molecules. Okay. The surroundings is everything else, so it includes the piston and the cylinder and everything outside the cylinder. As you recall in the first slide, we said energy is heat plus work. Well, the definition of work is energy used to move an object some distance. So, for instance, whacking a tennis ball with a racket is work. Lifting your lunch bag is work. You are moving something that has some mass over some distance. And the formula for work is force times distance. So you're moving something some distance. The other component of energy is heat. We call it Q. It's the other way of transferring heat. Here we have a Bunsen burner heating a metal paddle, and the heat is being transferred. Heat always flows from warmer objects to cooler objects. So even though you might think that when I throw ice cubes into my drink that I'm adding coldness to the water, in fact the warmness from the water is moving into the ice. It always moves from warm to cool or hot to cool. Be careful not to confuse heat and temperature. When something gets hot, it gains energy, the particles start to move apart, and that moving apart, that expansion is read on a thermometer. Okay? So the increased volume causes the mercury or the alcohol in the thermometer to rise. They're a little bit different. Let's just watch a little Eureka video on the difference between heat and temperature.
Temperature versus heat. Here's a bucket of hot water at 50 degrees Celsius. And here's a cup of freshly boiled water at 100 degrees Celsius. In which of these two containers are the water molecules moving faster? The bucket or the cup? That's right, because the degree of hotness of the water in the cup is much higher than the degree of hotness of the water in the bucket. And the hotter something is, the faster its molecules move. Would you say, therefore, that there's more hotness in the cup than in the bucket? In that case, if the water in your swimming pool is just a bit too cold for you, you'd be better off emptying the cup full of boiling water into it, rather than the bucket full of water at the lower temperature, wouldn't you? Or would you? You don't seem so sure. Let's do an experiment to find out. Suppose you had two identical swimming pools, one yellow and one blue. And suppose that the water in both of them was just a bit too cold for you. When you pour the cup of boiling water into the yellow pool, does the water feel any warmer? You can hardly feel any difference at all, can you? Now pour the bucket full of 50-degree water into the blue pool. How does that feel? Quite a bit warmer? Aha! So even though the water in the cup was considerably hotter than the water in the bucket, the 50-degree bucket water is much better at heating up swimming pools than the 100-degree cup water. Why is this? Well, let's look at the facts. The bucket obviously contains many, many more water molecules than the cup does. The temperature of the average molecule in the bucket is 50 degrees. And the temperature of the average molecule in the cup is 100 degrees. Now let's substitute something else for the molecules. Imagine that instead of molecules, the cup were filled with $100 bills, and the bucket with $50 bills. Which would you rather have? Each individual bill in the cup is worth much more than each individual bill in the bucket. But the total amount of money in the bucket is much greater than the total amount of money in the cup. It's the same with hotness. The degree of hotness, like the value of the dollar bills, is higher in the cup. But the quantity of hotness, like the quantity of dollar bills, is greater in the bucket. We've already seen that the word for degree of hotness is temperature. Now it's time to introduce the other word for quantity of hotness, which is heat. The water in the cup has got a high temperature, but very little heat. And the water in the bucket has got a much lower temperature, but a great deal of heat. Now you know why buckets of 50-degree water are better at heating up swimming pools than cups of boiling water. On the other hand, if you're looking for somewhere to dunk your tea bag...
Okay, so hopefully that showed you the difference between temperature and heat. Heat has this mass component, quantity component. Okay. So heat will always transfer until thermal equilibrium is established. So if I have something cold and something else that's hot that's next to it, and hot is being indicated by the long whooshies, which indicate movement, then the hot system will transfer energy to the cold system until they eventually become the same temperature, and the heat is evenly spread. Okay? Makes sense? So as we know, energy can be converted from one type to another. The cyclist on the hill has potential energy. As they come down the hill, she's got kinetic energy. At the bottom, all the potential energy that was had up here is now all kinetic. And you can see that in this chart here, the total energy is always the same. If this is kinetic energy and this is potential, at the top of the hill you have lots of potential. As you come down, that energy becomes converted to kinetic, which rises, right? But the total is always the same. If you hit a pool cue, you are going to cause that ball to hit another ball, and that energy, in this case work, gets transferred. So that energy is conserved is actually the first law of thermodynamics, and it says that energy is neither created nor destroyed. So if I start off at some initial state and I lose energy to that surroundings, then an equal amount of energy is added to the system from the surroundings, and they're always going to be equal. Whatever is lost from one system is going to be gained by another. So the total energy of the universe is a constant. Anything lost must be gained by something else. So the internal energy of a system is the sum of all the kinetic and potential energies, and we call it E. It's hard to measure, really can't measure the energy of anything. There's no energy-ometer, but you can determine the difference in energy, what happens to energy, by looking at the difference between initial and final energy. Excuse me. Okay. So, if we have a system that starts off low energy, and we end up with a higher energy at the end, we had to put energy in to make something happen. We call that an endothermic system. The final energy is higher than the initial energy. That's endothermic. Okay? So energy went into the system, and we feel that as cold. As opposed to starting off with some, let's say, reactants that lose energy to the surroundings and become products. So the final energy is lower than the initial energy, and this would be exothermic. The system is losing energy. So if we have changes in internal energy, when energy is added, is exchanged between the systems and the surrounding, it's either going to be as Q or as W or both. So change in energy is always Q, the heat change, plus the work change. So energy is heat plus work. Remember, heat is energy used to cause the temperature of an object to rise, and work is energy used to cause an object that has mass to move. Now, it's really important that you get the signs of Q and W straight, and these are easier said than done. It seems simple, but there's often a lot of confusion that leads to wrong answers and losing points on tests. Alright, so if I have a system and I have to add energy for something to happen, for instance, if I have this beaker of water and it's going to melt, energy is going into it. Now, the problem that people have is they think about this is if I were putting energy into this, this would feel warm, and in fact it doesn't. It feels cold. But because I'm putting energy into it here at Bunsen burner, the Q, or the heat, is gained. It's a positive. System gains heat. And I feel that as coldness. Okay? As opposed to the system losing heat to the surroundings, and I can see this beaker that I could tell is hot, right? And the Q is minus, right? And here the heat from the reaction inside the beaker is being transferred to my hand, and I say ouch because it hurts, right? So if I feel something getting hot, it's an exothermic reaction, and Q, or energy, is lost. Whereas if Q is positive, that means my warm hand is transferring energy to the object that's colder. Okay? So if heat is being lost, if heat is leaving the system, it's negative. If it's going in, it's positive. Now let's take a look at work. So here again I have my cylinder with a plunger. If I am pushing down on that plunger, work is being done on the system, so work is positive. Okay, so I'm adding work on the system by the surroundings. And on the other hand, if the molecules in here cause the plunger to go up, then the work is being done by the system on the surroundings. Work is lost, and work is therefore negative. So signs for delta E. If delta E is positive, that means there's a net gain of energy by the system, and if it's negative, it means there's a net loss by the system. So in the exchange of heat between system and surroundings, when heat is absorbed from the system, it's endothermic, right? Q is positive. Heat's going from my hand to the cooler object. When the heat is released by the system, I can see it. It's making the room around it warmer. It's exothermic. Q is negative. My hand hurts when I touch it. Okay? So let's take a look at a problem. We want to calculate the total energy change for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. So this is all about, seems like a really simple problem, but it's all about identifying if the changes are positive or negative. So we've got to look at the delta E is Q plus W and identify the sign on each of them. So Q is heat. It says it's an endothermic process, which means that I'm adding 15.6 kilojoules. Endothermic tells me Q is positive. And it also says work is being done on the system, so work is being added, so work is also positive. So as a result, my delta E is a positive 15.6 kilojoules of Q plus 1.4 kilojoules from work, gives me a total of 17 kilojoules. The other thing that becomes important for energy is understanding the concept of state functions. So, like I said, there's no such thing as an energyometer. We have no way of identifying exact internal energy of a system, but we can look at how a system, where a system came from, the change in energy. Okay? So we know that internal energy is independent of the path. So if I have 50 grams of water at 25 degrees C, which is about room temperature, the energy in that water, in that system, doesn't matter whether it started off as 100 degrees C and was cooled, or whether it started as ice at 0 C and was heated. Okay, so it doesn't matter how it got there. So internal energy is a state function. And a state function only depends on the present state and not the path it took to get there. So for instance, here I have a battery and I have it in a closed loop, which means that the battery is just going to run. It's going to create a lot of heat. So the charge to the discharge produces heat, just Q. Whereas this battery is attached to a fan. So as you know, the battery itself will get warm, right? And work will be done. So it's both heat and work. But the total energy is the same in both cases. So while energy is a state function, Q and W are not. So whether the battery is shorted out or discharged by running the fan, its delta E is the same. So let's take a quick peek at this little tutorial. Alright, so let's Alright, to study the internal energy, we have to identify where energy exchange is occurring. Typically this involves defining the system and the surroundings. So in this case, my system is what's happening inside the flask. I've added some chemical to something else. It looks like it's generating heat, causing a rise in temperature to my surroundings. Okay, so my system is what's going on inside the flask. Surroundings is everything outside of that. And energy is being transferred. So the sum of the potential and kinetic energies of all the particles is the internal energy. When an exchange of energy occurs, there's a change in internal energy of each. So the internal energy of the system, if it goes down, then the surroundings will do the opposite. So those surroundings will rise in energy in equal amount to that loss from the system. Okay, energy is conserved. So if I have a system and surroundings, as one goes up, the other goes down. They are inversely proportional. So if I increase the temperature of the surroundings, I decrease the temperature of the system, and on and on. So we know that delta E, change in internal energy, is Q plus W, heat plus work. So if I put a beaker of ice cubes out, the energy goes up. It's being absorbed by the system. The temperature is rising. Okay. Same amount of energy taken away, removed, will cause the opposite phase change to occur. Alright, so here another system where we can look at what's happening with work. So here we have hydrochloric acid, put a piece of metal in it, they're going to react, it's going to produce a whole bunch of hydrogen gas. That gas will expand and causing pressure on the piston and causing pressure being done on the surroundings. Okay, so here's work being done as a result of a chemical reaction. So let's take a look at this. So we have the system receives 575 joules of heat and delivers 875. So if it's it receives 575 joules, so that's a plus, and delivers 875 to its surroundings. So it's going to be plus 575 minus 875, so the difference is going to be negative 300 joules. Okay. Let's take a look at another. When gasoline burns in a car engine, carbon dioxide and water vapor are produced. If these expanding gases do 450 joules of work on the pistons and the engine loses 330 joules to the surroundings, calculate the energy change in kilocalories. So I can take the expansion of the gases does 450 joules of work on the surroundings, which include the piston. So this is going to be a negative, right? And the engine loses 330 joules to the surroundings as heat. So this will also be a negative. So it's going to be a total of negative 780 joules. And if I convert that to kilocalories, I'll just show the work here so you can see how that was done. So the total loss is minus 780 joules. If I convert that to kilojoules and then to kilocalories, I end up with minus 0.186 kilocalories. Okay, let's take a look. You can go back to that tutorial. It's on my link to it is on my Moodle page and do some more problems. Okay, so when we look in, most of the energy changes in chemical systems come from heat, as you can imagine. But there is some work done, and that work is called expansion work. The only time work is done in chemical systems is when we have expansion work, and it always involves gases, and we call it PV work, pressure volume work. And the formula is work is minus P delta V. Okay, let's just take a quick peek at this animation here for pressure volume work. So here we have, this is actually what goes on in a catalytic engine, right? So we have gasoline being injected. That gasoline, there's a carburetor, causes a spark, causes the gas to vaporize, and that does work. As it does, it pushes the piston. And this moving of the piston is what causes the car to work. And we call this P delta V work, right? P change in V. So it takes work to change the volume of a gas against the outside pressure. Now in this formula, pressure is the outside pressure, outside the container. Work is in joules, and V is volume in liters. So in an internal combustion engine, gasoline enters the chamber, gets compressed, causing it to ignite. That ignition, it causes it to expand, drives the piston, and the whole process keeps on going. So work can be defined as the product of force times distance, or as the product of pressure times change in volume. So this is just a little animation to show you how this and this really are the same thing. Pressure is the same as force over area. So if you replace that in the equation, you get this. Volume is the same thing as the distance cubed. And area is distance squared. Those will cancel out, and you have force times distance. Just shows you how we arrived at work equals pressure delta V. Alright, so if you want to come back here and take a look at these problems, you can do that. But we're going to go ahead and move on. Okay, so usually if we have an open container, which we usually do when we have a chemical reaction going on, the only work that gets done is by a gas pushing on the surroundings. Okay, so if we're making a liquid or we're making a solid, volume does not appreciably change, and therefore the pressure doesn't change. Okay, so the only time we have this happening is when we've got a gas involved. Okay, So we can measure the work done by using, here's a manometer that's used to measure the pressure of a gas. If it has a piston on it, then we can actually measure the rise in the piston, which tells us the change in volume. And if we apply the pressure in the surroundings, we can calculate the work that's done. So let's take a look at this one. We want to calculate the work associated with the expansion of a gas from 46 liters to 64 at a constant external pressure of 15 atmospheres. So our formula for work is minus P delta V. Minus P is pressure is 15 atmospheres. The pressure change final minus initial is 64 minus 46. If I plug that in, I get 270 liter atmospheres. Okay, so there's more of these problems here if you wanted to come back and take a look at these. Okay. So a balloon is being inflated to its full extent by heating the air inside. In the final stages of this process, the volume of the balloon changes from 4 times 10 to the 6 liters to 4.5 times 10 to the 6 liters by the addition of 1.3 times 10 to the 8 joules of energy as heat. Assuming that the balloon expands against a constant pressure of 1 atmosphere, calculate delta E for the process. And it gives us some conversions here. So we know energy is a combination of Q, heat, plus work. We can change work and fill in for it minus P delta V. Q is given to us here 1.3 times 10 to the 8 joules. Minus P, the pressure is 1, so that's minus 1 times the change in volume. So I went from this to this, so I just subtract these two. Okay. When I do that, I have this Q in joules for my heat, and this is my work. Now their units are different, so I've got to get this liter atmospheres converted to joules, and it gives me a conversion factor here, right here to do that. 1 liter atmosphere is 101.3 joules, and when I do that, I end up with negative 5 times 10 to the 7th joules. It's important on these problems that you always indicate the sign of the energy. It's a common area where students lose points. Okay, so this is the energy associated with the work, and if I add that to the heat, the energy from the heat, I get a total of 7.9 times 10 to the 7th joules. Okay, so enthalpy. Let's talk about what enthalpy is. So we know that the change in energy is Q plus W, heat plus work, and we know that work can also be expressed as minus P delta V. So if I have a constant volume, this is going to be 1, right? And, well, this will be 0. It would be P times 0. Delta V would be 0 if it's constant volume. So that would make delta E and Q the same. If I have a constant pressure, then Q is delta E plus P delta V. So if we look at this, this is the heat exchange in a reaction at constant pressure. And because it's so important in chemistry, it has its own special term, and it's called enthalpy, and has the value of H. So H, enthalpy, is the energy plus the PV work. Okay? And we generally measure enthalpy by looking at the enthalpy of the products minus the enthalpy of the reactants. So let's talk about what's the difference between energy and enthalpy. So I'm just going to give you one example, but most reactions are this way. So here we have a reaction where we have propane combusting, right? And we have a delta E, it's a very exothermic, of negative 2,000 kilojoules. And this is when it's done at constant volume. If I do the same reaction at constant pressure, I get almost exactly the same amount of energy, okay, as my enthalpy. So my enthalpy and my energy are almost identical. So the P delta V is tiny. We're talking about the difference of 2 kilojoules, less than 0.1%. And that little bit of pressure times change in volume comes from the fact that I started with 6 moles of gas, and in the products I have 7 moles of gas. Okay? So the key point, and this is true of most reactions, is the difference between enthalpy and energy are tiny, so that they're nearly equal. So when we're talking about the energy involved in chemical reactions, we are almost always talking about just enthalpy. So if we have constant pressure, the change in enthalpy is either going to be the heat gained or lost. It's generally expressed in standard state conditions. Now this is different from STP, where we talked about gases last year. The big difference is standard state is 298 K, which is about room temperature, 25 degrees C. They are both at 1 atm, and if we have a solution, we assume 1 molar. So standard state assumes room temperature, standard pressure, in 1 molar. A little different than STP. It'd be cooler. You need a jacket if you were at STP. But standard state, pretty much what's happening in the lab. So a process is endothermic if the delta H is positive. If I'm adding heat, a process is exothermic when delta H is negative. It's losing heat. A few things about enthalpy. It's a state function, which is useful in problem solving. It doesn't matter how it got to its state. Okay, it doesn't matter the path that it used to get there. If we're at constant pressure, the enthalpy and heat are exactly the same thing. That's another important relationship. Okay. Delta H for a reaction in the forward direction is going to be equal in size but opposite in sign to the enthalpy for the reverse reaction. Something also very useful in solving problems. It's important to know what states of matter we're talking about when we do our calculations. And we can calculate enthalpy, or the change in enthalpy, from several sources. We can use stoichiometry or calorimetry, which is actually collecting experimental data, which you'll do in the lab. We can use tables of standard values, which you'll find in your textbook. Or we can use Hess's law, which we'll learn all about. And we can also use bond energies. Okay, so let's take a look at a problem. Upon adding solid potassium hydroxide pellets to water, the following reaction takes place. So I have potassium hydroxide solid becoming potassium hydroxide aqueous. So this is just the heat associated with making a solution. And it says plus 43 kilojoules per mole. So what that says is, in addition to this being produced, I'm also producing heat. Okay, so the question is, if I'm starting with 14 grams of potassium hydroxide, does the beaker get warmer or colder? Well, since I am producing heat, it's going to get warmer. H is written as a product. It's leaving the system. So is it endothermic or exothermic? If it's leaving, it's going to be exothermic. And what is the change for 14 grams of KOH? Now, almost always when an enthalpy is provided to you, it's going to be in either kilojoules or joules per mole. Okay. So if I know how much energy I get for a mole of potassium hydroxide, I can adjust that for something less than a mole. So I know the molar mass of potassium hydroxide is 14 grams. Or I'm starting with 14 grams. Its molar mass is 56.1 grams. I have 1 mole of potassium hydroxide. And I know that's 43 kilojoules, and I end up with 10.7 kilojoules for that 14 grams. Let's take a look at this one. How much heat in kilojoules is evolved when 5 grams of aluminum reacts with a stoichiometric amount of iron 3 oxide? Okay, so these kilojoules we're going to assume is for a mole. It doesn't say it here, but we're going to assume that it's for a mole. So we got 5 grams of aluminum, okay, and this is my enthalpy. Now this is written different from the last one. If you notice the last one, it didn't show the delta H. Now what this says, it doesn't show energy as a product. What it shows is delta H is a negative value, okay? Which means it's exothermic. If we go back to the previous chart, here it shows the energy as a product, and you have to decide based on that, is that exothermic or endothermic? And if energy is being produced, then this is exothermic. Now if I were to written this as delta H is 43 kilojoules, I would show it as a negative 43 kilojoules for delta H. Okay? See the difference? If I were showing this as a product here, and I didn't have this delta H, and I just had plus, I'd have plus 851.5 kilojoules. So there's two different ways of showing it. You've got to be sensitive to which one you got. So if I only have 5 grams of aluminum, what I know is, based on the molar mass, is that's how many moles I have. And if I have that many moles, what I know is 2 moles of aluminum will produce this much energy. So that smaller amount produces just 78.8 kilojoules. Okay, so it's basically a little stoichiometry problem. So when we're talking about the enthalpy of chemical reactions, we can generally only measure the change in enthalpy. Okay? And since it's a state function, it doesn't matter how we got there. So we can use several different sources. Okay? So the change in enthalpy is the enthalpy of the products minus the enthalpy of the reactants. And a lot of these values are published. You can find them in your textbook. Okay? So if I'm starting here and I am producing this, okay, it's losing energy, right? Losing 890 kilojoules. If the reaction is going the other way, then I am gaining 890 kilojoules. So delta H is called the enthalpy of a reaction or the heat of reaction. That's where the H comes from. If it starts high and ends up low in energy, enthalpy is, this is exothermic, right? Alright, so we're going to stop there. Talk about calorimetry next.